All right, so I wanted to look at the state estimation problem and show how you already know how to do it if you've been taking the fundamentals of machine learning class. And I want you to get an intuition for how to use it, where it comes from, and what the motivation is in the opposite order. So we'll start with the motivation. Why do we actually care? So if we have some vehicle moving around in space, and for this example, this is a satellite that we want to locate the specific position of very precisely for rendezvous maneuvers or just to make sure it doesn't, say, collide with anything. We have some internal estimate of how fast the spacecraft is moving and which direction it's moving in. So we can estimate internally by doing an integration, by propagating the next time step, in simple terms, some velocity times a time, gives you some change of position. Or we can do something more complex and do a mini support point integration. But in principle, we can use our internal measurements to have some internal estimate of our position, right? But that will drift over time. There is noise in our sensors, and as we accumulate noise and we deviate from the true position, which we'll say is this cosmic color line, this black estimate here from our internal sensors will slowly drift out of sync. And this error can grow very large. So we need to periodically take measurements from external sources, right? In this example, these red satellites are supposed to be GPS beacons. And we can measure our range to the GPS beacons. And based on our range, we can update what our estimate for position should be. So at each point in time here, we can measure the range to the satellite and correct our internal estimate. All right, so we have this cosmic colored line here. So the basic idea of the Kalman filter, which is what this piece of mathematical technology is called, is to take these red measurements from external sources and combine them with your internal measurements in order to best approximate whatever your true underlying state here is. So we're finding a weighted combination between this red dot and this black dot that will get us as close as we can to this cosmic colored dot. And the way we're going to do that is by turning it into a maximum a posteriori estimation problem, where this black line, our internal measurements and our internal model of how we're moving, is the prior probability, and our red measurements, these measurements of the external signals, are our data likelihoods, right? We'll get more to those specifics in a second. I want to cover one more motivating problem to help you solidify the idea. A similar idea would be you've got some robot in a room. This is almost exactly the same setup. Some robot that's rolling around in a room, starts in the corner of the room, so you know its start position, but it doesn't have a perfect sensor, and it doesn't have a perfect model of its dynamics. It'll start in the corner of the room, and it will model based on how its wheels are rolling, how many revolutions of its wheels it does on its left side and its right side, and it will estimate where it's gone within the room, right? It'll estimate we've gone to this through this trajectory. Perhaps we've gotten something close to it, but not quite. Something close to it, but not quite. This cosmic colored is supposed to be representing the true underlying trajectory. And then we measure our distance to the corner of the room from this point. So a Kalman filter will allow us to take this estimate of distance and combine it with this prior probability, this prior estimate of our position from the wheel motion and the internal dynamic model, and find a weighted combination between these to get us as close as we can, or to the underlying true trajectory. All right. So on the right-hand side of the screen, I have here some terms that I'm going to ease you into for the rest of this derivation, so it's not just a sea of letters. I'm going to refer to this underlying state as X, right? So in this case, this underlying state would be the cosmic line. We can't actually measure this because our sensors have noise, both on the sensors that are reading the red external signals, and there's some uncertainty in our dynamics, right? So let's say we're measuring the rate of rotation of the wheels. There's going to be some measurement noise on the wheel rotation rate. And that'll accumulate error over time. Z is our measured quantity. And it is going to be these red measurements here. So if we're measuring to a GPS beacon or measuring to the corner of the room, those will be external measurements that we use to update our estimate of our position. When I add a subscript T to the bottom right-hand corner, I'm saying that I'm looking at this quantity at time T, all right? So X sub T, the underlying state at time T, and similar idea for the measured quantity. When I put a hat on something, it means it's our estimate of that quantity, right? So we cannot actually measure X, but we will be estimating X hat as best we can. X hat is our estimate of X, right? So we do know X hat and we do know a Z hat exactly, right? Those are our estimates. So when I write something that is X hat sub T bar T minus 1, what I'm saying is the estimate of X at time T based on the information we have available up to the time step T minus 1. So at each of these, we'll have some discrete time step. This will be a discrete time Kalman filter. T0, T1, T2. Let's be consistent. T equals 0, T equals 1, T equals 2, right? So our estimate at T equals 2 is going to be based on the data we had at T1, and then we're going to propagate it along our dynamics model, along this black curve. And then once we get to T2, we're going to update our estimate for our position using the sensor that we sample. All right, cool. So I'm going to draw a little diagram of the underlying process to help solidify it a little bit, but I hope you're all following so far. So in general, we're going to have some initial state, some initial estimate for our state. We have some model of how the state progresses from one time step to the next, which is going to be represented by this function, f. I've labeled a subscript f sub 0 here. This function of x can also change with time, so we can have a different function at each time step. So this function f progresses us from x at 0 to x at 1 to x at 2 to x at 3. And this function g is how we read out our measurements from the state. So there has to be some dependence of the measurements on the state. Otherwise, if they don't share any information, we can't get information about our underlying state from the measurements. So the measurements are some function of the state. Cool. So we advance in the time step, starting from some estimate for our initial state. And then we read out some measurement at the next time step. We advance to the next time step. We read out a second measurement, and we can continue like this for an arbitrary length of time. Now, I want to show you the form of the solution now, and I believe it'll be elucidating if we go through and discuss the intuition behind it. All right. All right. So the solution for that we're pursuing in this lesson is going to be of this form. Our estimate for the underlying state at time t with the information available at time t is going to be equal to our prior estimate for the underlying state at time t that we made at time t minus 1 at the previous time step, plus some update gain, k. We can recompute this at each time step. and it will be a gain on a new term, which will be the difference between what we actually measured at that given time and what we thought we were going to measure at that given time. All right. So you'll sometimes hear this referred to as the innovation. And this is just error in our prediction. Error in our prediction. All right. So we update our estimate based on some error in prediction and a gain term. Cool. So that is satisfying to think of. What's wrong? Okay, cool. It's just Microsoft freaking out. That's satisfying to think of based on its simplicity, but I haven't actually shown you how to derive it yet. So let's get a little more intuition here. This K, this gain term, is going to have what kind of units? Take a second, pause the video if you need to, and go through and derive what kind of units it's going to have. So it's a linear term. It's going to have units of X units per Z units, right? Because X has some set of units, Z does too. It's a linear term, right? So it's going to have dimension X units per Z units. And let's think about this in terms of uncertainty. As our sensor measurements get more uncertain, let's say we have less reliable sensors, higher noise, what should our K term do as we get noisier sensors, ones that are less reliable? Pause the video and think about it. So as we get less reliable sensors, this K term should go down. Decreases with less reliable sensors. All right? Because as this K term increases, we favor the innovation more. Right? So if it's very large, most of our guess for what X is at time T is going to be based on the innovation. And as we get less certain about the state of X, let's phrase it like this. As our uncertainty in the state of X at the previous time step increases, so as the uncertainty in this estimate goes up, what should happen to the gain K? All right. So as we get less certain about our previous estimate, we should rely more on our innovation. So our gain is going to increase with less reliable prior estimates. Cool. So we have this notion that we have X units per Z units, and we have this notion of trading off between reliability. We're weighting, in our previous example, we are weighting between these black dots and red dots. So if the red dot is more reliable, we favor it more. And if the black dot's more reliable, we favor it. All right. So let's, based on this intuition and some dimensional matching, let's play with the intuition of a Kalman filter. So let's quantify the reliability of the sensors by saying R at time T is the second order dispersion, the covariance of the innovation. It measures how far away from the zero center all the measurements tend to be spread. Right? So if we call it this, we call that R, how reliable our sensors are. This is a covariance. It's a second order measurement. If you've been in the machine learning class, you should be familiar with this. This is the variance matrix that you see in Gaussians. which will come up in a second. And then if we have, we'll call this sigma at time t, given the information at t minus 1. So this is the uncertainty in our measurement for the prior state is going to be this. So the expected value of the difference between the true underlying state second expected value of the second order moment of the difference between the estimate from the prior and the true underlying state, right? Something like that. So we want our K to look something like this. We'll have, yeah, sorry, let's call this S instead. Just, I use R somewhere else in the later part of the derivation. That's the only reason why. And I don't want you to look at your notes coming back here and say, whoa, how did that get there? After you've already seen the entire lecture. Right. No, I mean, this shouldn't be too much of a lecture. This should be something you participate in a little more. All right. So what we're saying is the gain is going to be proportional in some sense to the covariance of our error in our prior estimate, and the inversely proportional to the covariance of these innovations, right? And notice this is going to have what kind of units? The x units squared. This will have what kind of units? This will have 1 over z units squared, right? So we're going to need some correction term to get it back into these units here. And what that correction term is going to come from is the relationship between x and z, right? So we need some coefficient term that'll be, we'll call it some c. Here, let me take a second to think about how I want to introduce this. Okay, so we have our x units squared per z units squared. And we're looking for some term to get it to x units per z units. So we'll have dimension z units per x units, right? Cool. So if we're looking for the change in some z units per x units, let's say we have z as a function of x, right? That was based on the little model that we codified up here. Cool. A given time step, t is a function of x at that time step. This is just saying same thing, except at a specific time step. We'll do a linear expansion. Say this is approximately some reference value for z. Call this z ref plus some change in this function per unit change in x evaluated at time t for a given change in x, right? And so when we're looking at the difference between z and some reference z per unit change in x, we're looking at a linearized model of how our measurements change with the state. So we can use this to get a matrix. We'll say that z is approximately c at time t of x, right? So we'll say this is evaluated to be c, all right? Decent. This is our measurement model. And so we'll get a Kalman gain. That is the uncertainty in our prior times some term that describes how z changes with x, how the measurement changes with the state, and then divided by the uncertainty in our measurements. The distance from what we predicted we would measure and what we actually measured, right? And then we look at how tightly or loosely distributed that tends to be. So very reliable sensors have a very low covariance for S. So reliable sensors will be divided by a small number and cause this to be a large Kalman gain. Very unreliable prior estimates will do something similar, where this matrix will be very large, but the opposite is true. If this matrix is very small, our prior estimates are very reliable, very clustered. Our prior estimates are very clustered around the true value, then this quantity will be very small. So we'll rely a lot more on our prior estimates for the update. All right. So that's some, I hesitate to call it a derivation. It's more of an intuition. So you don't have to follow it perfectly, but this will help you see where everything's coming from, right? Uncertainty in our prior, relationship between our state and our measurements, and uncertainty in our measurements, right? And if you need to, go and review the concept of covariance. Okay, so now we've looked at the final form of the solution. We've discussed the intuition behind it. And now we want to look at this as maximum a posteriori estimation. All right. So to pose the Kalman filter problem as such, we're going to seek the argument X estimate at time t using information available at time t that maximizes the probability of X at time t using the information available at time t, given our measurement at time t, right? So in this case, I'm saying that I only want to maximize my estimate here under the most recent measurement. So what I'm saying is this chain here only links 1 to 1. We don't have X1 affecting the state of X3, which is how most physicals, well, I hesitate to say most, that's how most vehicles work, right? If you drive up a mountain and then drive down and crash into a wall, it's the same thing as if you just directly crash into a wall, you end up in the same position. That's all that's saying. I want to maximize the probability of my estimate given my most recent measurement. My estimate for the state given my most recent measurement of something that depends on the state, right? So what do we recall from Bayes' theorem? How can we phrase this in a tractable form? Take a second, write it out. Pause the video and write it out. You'll get nothing out of this if you don't do that. You have to like put some skin in the game. Otherwise, it doesn't make any sense. Or, well, no, it can make sense, but it'll go in one ear and out the other. It'll just be a cool thing that you heard once. Right? But it won't stick. All right, cool. So if we're looking at Bayesian estimation here, we can have our data likelihood being the probability of our measurement given our prior. So how likely was this measurement to occur if this prior is true, right? How likely do we think this prior is? Just apropos of nothing. So what this really is going to be is this prior will be based on our previous estimates. So hidden in here, sort of like how we have when we're searching for parameters of a Gaussian distribution, we can adjust the parameters of, I believe it's an inverse gamma distribution to search for where the mean and variance could be. We'll search for where our prior estimate of the state is based on where we thought it was going to be before, right? Based on data from the previous time step, right? So phrase it a little more tractably, because I understand we're starting to get completely away from physical drawings and into just letters on a page. If we are following along with the vehicle, we measure our position here. Then we propagate it internally. We estimate our position to be here. What we're saying is if a sensor tells us we're out here, and let's say that would have required us to go 700 miles away in only 1 second, we can't reasonably treat that as equally likely, right? So instead of having a uniform prior here, we say that there is some Gaussian distribution around this propagated state. So here will be x at time t minus 1, given the data we had at t minus 1, and we'll have some x at t estimated based on the data we had at t minus 1. And the way we get from here to here is going to be our dynamics model. But this is how this connects to MAP estimation. This is where I would be asking for questions if I had people here that yeah. All right. Cool. So this is the maximum a posteriori estimation. Send me questions on Slack if you have them. Now, notice we're looking to optimize with respect to this state estimate, right? The probability of a measurement occurring among all state estimates is going to be integrated. The state estimates will be integrated out of this probability here. This denominator does not depend on the state estimate, is what I'm saying. So we're going to argue that this is equivalent to optimizing just the numerator, right? And I won't make you sit through me rereading all of that. All right. I'm arguing that we can just optimize the numerator. Denominator does not depend on the quantity we're trying to optimize for. Okay. So now I've hinted at this a little bit before. We're going to discuss what these probability distributions actually are. So we're looking at this, the probability of the measurement given our estimate, and the probability of our estimate under our propagated dynamics model. So we need to discuss what these look like. I'm going to say Gaussian distributions are a good estimate, right? So as we move along this trajectory from our previous state, we'll get to some new estimated state, and we'll probably have some noise around where that state is. There'll be a blob of uncertainty as to where we actually are, but we'll be in the neighborhood of what we guessed. And on average, I'm going to argue that our dynamics model will put us on average where we should be. So it may vary to a little to the left, a little to the right, depending on this specific time step. But as you take samples overall, we'll tend to zero error. That is to say, the expected value of our estimate of the propagated state minus the true underlying state is what? 0. So that is going to be one of the first points when I'm describing these distributions. And then when I take out these measurements, right? So I'll scroll back up to this picture I had. When I make these measurements of Z based on the underlying state, I'm going to say my sensors have some noise, right? So they may not always get the true underlying Z. In fact, we expect them to never do so. But they'll be measuring something that's close. And as we average out these measurements, they'll all tend to the true underlying Z. So I'm saying the noise here will also be Gaussian on the sensors. So a probability distribution of our measurement of Z. Yeah. Being what we're actually reading out, right? So our sensors are noisy, but they have Gaussian noise. And we're saying it's white Gaussian noise. It's not at a constant offset, right? So as we continue to take measurements, the measurements will all tend to average out. So let's take this model And now let's phrase what our dynamics model and our measurement model look like. All right. So our dynamics model will be x at time t is equal to f at time t minus 1 of x at time t minus 1. Right. And our measurement model, z at t equal to g t of x of t. Now I add in the noise terms. So I'll call this noise x plus noise z. And I said we were doing white noise. So nx is going to be distributed how? And similarly for measurements, these will also be distributed with white noise. What are these quantities and these quantities? Make sure you know those. It's the mean and covariance, right? So covariance Q describes how, I guess you would say, strong the power in the noise signal for the state, power in the noise signal for, and R describes the power in the noise signal for Z, right? So a large Q, we're saying that our estimate for the dynamics for the update at the next time step is not very good, very unreliable. It still tends to go to average out, but this distribution of the true underlying, this distribution of our estimate for the true underlying system is going to be very spread out. All right, cool. So you'll often hear these referred to as process noise, and measurement noise. All right, cool. So I think I'll finish up the first video by describing the distributions of these two bad boys. And so we'll have an objective function that we can optimize, and we'll pick up the optimization in the next video. All right, let's finish up here. So we take our process noise, measurement noise, we're quantifying our uncertainty. Our data likelihood, that is the probability of our measurement under our estimate, is going to be the measurement probability density. So our point estimate here, the average for it, is going to be whatever our measurement function is using our optimal estimate for the state, right? As the input to the measurement function, and then we'll take that value as the central estimate. Prior probability is going to be a probability, a Gaussian placed on the point to which we are estimating we will propagate, right? So if we look at this dynamics model for how we update the underlying state, we'll take our estimate from the previous time step, we will propagate it one time step, we will get what I'll refer to as the estimate at time t using information from t minus 1, right? And that will be our prior probability for what t, x of t, given the information at t is. All right, cool. So do you guys remember the formula for multivariate Gaussians? It's okay if you don't, but if you take Dr. Boo's information theory class, you'll need it. All right, so throw it up on the screen here. Let's see if I can do it. I can probably still do it. ZT given x, t, t, equal to 2 pi raised to negative the dimension of this variable. So it'll be the dimension of z by 2 times the determinant of the uncertainty in this Gaussian. Which quantity is going to be the covariance of this Gaussian? Pause and think about it. Do you see why? It's the measurement uncertainty. If not, message me on Slack. I know I'm tilting away from the camera here. I'm not. It's just the way it is from time to time. Hold on. Right. Still doing multivariate Gaussians centered on the measurement model. I just had to move everything down here to make sure it wasn't running off the page. All right, cool, cool, and cool. So this is our probability density here for the data likelihood. And then for our prior probability, we will be using previous estimate, right? I'll refer to that as the estimate of the state at time t using information available at time t minus 1. X 2. So dz and dx are dimensions of z and x respectively. Right. And what is the covariance for this? So B, actually, that's actually a fair point. The covariance is going to be written like this. I will define this in a second. We'll show how covariance updates works. All right. -1/2 exponential -1/2. It's the difference between underlying t and our propagated value. This one. Inverse. Oh man, I'm running out of room even on the wide space. But you know how quadratic equations work. It's just a quadratic in the numerator. And transpose can fit it just barely, just barely. All right, so here z is some vector. We'll keep it real for now. Dimension z. And the state is going to be some vector of dimension dx. So we're doing column vectors here. All right, cool. So I promised you I would describe what's going on here. So we start out with every estimate having some measure of uncertainty, right? We discussed this over here. This is the covariance, the second order dispersion of our estimate of the state at time t given t minus 1. You'll see that as we apply the dynamics model, we'll have to update our estimate because with the imperfect information of our dynamics model, the uncertainty that's implicit in this variable or in our estimate at time t minus 1 given t minus 1, when we propagate that forward, that estimate tends to grow, and we have additional uncertainty due to this process noise. Sorry about that. I don't know how long that was hanging there. Due to this process noise, right? The nx. So we have some uncertainty just due to propagation. Even if we had perfect propagation, the uncertainty bubble widens. And we have additional process noise, which will continue to add uncertainty at each time step, right? So this is the second order dispersion of this quantity. Right? I should hesitate to use the term dispersion. You have to check. That might be a technical term used somewhere else. Right. This is the variance, second central moment. Right. So we have these quantities, and if we want to find the argument that argument x of t given t that maximizes them, what can we do to help simplify these? Because we're going to take the product of these and then ostensibly take a derivative. What's the trick that we're going to use when we take this producted with this in order to make it tractable? That is, you better pause it and think about it if you don't know. The logarithm. So we're going to take our objective function to be the logarithm of this product of this data likelihood and this prior. Right? And notice that once we take the logarithm, we have the terms that are currently being multiplied being added. Terms can come out of the exponent and become multipliers. And when we take the derivative of this, dl d del x hat and t sub t equals 0 in order to do the optimization, all the terms that are additive and do not depend on the quantity we're trying to optimize, what's going to happen to them? They're going to go away. We won't have to worry about them, right? So you've done in this class an optimization like this, showing the interchange between Gaussian fitting, maximum probability estimation on a Gaussian and least squares optimization. This is the exact same math, just in a higher dimensional space, right? So we have covariance matrices instead of just sigma squared. But if you don't believe me, go through, do the math yourself. What we're going to get is an objective function. How do I phrase this? How I phrase it. The argument that maximizes this objective function is the same argument that's going to maximize this. An exponent of this term and this term added together. So I'll see if I can't get copy and paste in my favor. See if I can snake this lasso select. Yes, let's go. Can't do that. Piece of paper. All right. And then this bad boy also going to come here, right? Nuts. Just like that, skip forward 10 seconds, something like that. You can see where I succeed finally in doing this. No. Oh. Right. And we take the natural logarithm of this. So when we take the natural logarithm, logarithm being a monotonic function, if you have some increase in its argument, you have an increase in the logarithm. So if you have an extremum in its argument, you'll also have an extremum in the logarithm. All right. So that is equivalent to the argument that maximizes just the term in the exponent. And you see we have a negative and a negative here. So you guys okay if I turn this to a positive and I turn this from a maximizing to a minimizing? What I'm doing is I'm taking a parabola that's facing upside down. We're trying to maximize it. I'm saying flip that over the x-axis and minimize it, and that will occur in the same place. Cool? Cool. And now I'll take these terms. Copy that. Throw that down. And this other term. It's also in our little objective function. Objective function. Again, skip forward 10 seconds to where I successfully copy and paste. This is my greatest trial. It's the hardest thing I've ever done. Copying and pasting. It's because my life has been too easy so far. All right, cool. So we have this objective function now. We're looking to minimize this quantity. And you may recognize this as a least squares problem. So next time, we're going to get into how we find the least squares solution to this. And we'll show that we can also propagate our uncertainty. We do uncertainty updates. By uncertainty, I mean covariance, right? All right, so please Slack me if you have questions. I wanted to bring this up. The Kalman filter is everywhere in my field of work. I was astounded that I never heard of it until I came to grad school, because it's in anything that has to make online updates. It's sort of a principal way of updating estimates online. Started the discussion with this. Point being, if you're working on cars, if you're working on airplanes, if you're working on spacecraft, if you're working on anything that is has a linear model that needs to constantly update parameters, this is the way to do it. You'll be glad you know about it. All right. Peace.